Hello everyone. Today we shall discuss about vector calculus. Under vector calculus, we shall study about gradient of a scalar field. So before I go to the gradient of a scalar field, we shall discuss about an operator which is called as a del operator or nabla operator. So this symbol is referred to as nabla. The operator del is called vector differential operator, which is defined as del is equal to dou by dou x into I cap plus dou by dou y into j cap plus dou by dou z into k cap. So dou by dou x, dou by dou y, dou by dou z are partial derivatives with respect to x, y and z. This operator needs to be always operated on a scalar function. So when a del operator is operated on a scalar function, the output which we get will be a vector. So gradient of a scalar field. So as I already mentioned, the del operator needs to be always applied on a scalar function, say phi. So gradient of a scalar field is defined as if phi of xyz is a scalar function of three variables and phi is differentiable, then the gradient of phi is defined as grad phi or del phi or nabla phi all represent dou phi by dou x into I cap plus dou phi by dou y into j cap plus dou phi by dou z into k cap. So dou phi by dou x is partially differentiating phi with respect to x, keeping y and z constants. Dou phi by dou y is partial derivative with respect to y, treating x and z constants. Dou phi by dou z is a partial derivative with respect to z, treating x and y constants. So phi is a scalar function and we are applying the del operator or gradient on the scalar function. So the output what we get is a vector function. What is the physical significance of the gradient? Gradient of phi gives us the direction of maximum rate of change of phi at a particular point, whereas minus grad phi, it points in the direction of most rapid decrease of phi. Let us look at an example as to how we find gradient of a scalar function. So if phi is equal to x square yz cube plus xy square z square, which is a scalar function, determine gradient phi at the point 1, 3, 2. As we already know, gradient of phi is equal to dou phi by dou x I cap plus dou phi by dou y j cap plus dou phi by dou z k cap. So we shall first find dou phi by dou x, dou phi by dou y, dou phi by dou z. So dou phi by dou x is partially differentiating with respect to x, treating y and z constants. So derivative of x square is 2x, yz cube is written as it is, derivative of x is 1, so it remains y square z square. Now dou phi by dou y, treating x and z constants and partially differentiating with respect to y, we get x square z cube plus 2xyz square. Dou phi by dou z is the derivative of z cube is 3z square, x square y is retained as it is, and derivative of z square is 2z, and xy square is retained as it is. So these are the partial derivatives dou phi by dou x, dou phi by dou y and dou phi by dou z. So gradient of phi will now become, so substituting the values of dou phi by dou x, dou phi by dou y and dou phi by dou z, we get a vector function. So since they have mentioned to find gradient of phi at a particular point 1, 3, 2, just substitute x is equal to 1, y is equal to 3 and z is equal to 2 in gradient of phi. So substituting the values of x, y, z and simplifying, we get the gradient of phi as 84 I cap plus 32 j cap plus 72 k cap. Properties of gradient. There are three important properties of gradient. So if f and g are scalar functions, then gradient of f plus or minus g is gradient of f plus or minus gradient of g. Very much similar to derivatives. So if I have d by dx of f plus or minus g, so it will be derivative of f plus or minus derivative of g, g of x, say. So coming to the gradient of fg, just like using the product rule, g into gradient of f plus f into gradient of g. Gradient of f by g, just like the quotient rule, denominator square, denominator into gradient of the numerator, that is gradient of f. So this should be minus f times gradient g. So it is denominator square, denominator into gradient of the numerator minus f times gradient of g. So this is the grad properties applied on two scalar functions. Thank you.